especially kind of technical, dense text, also not very readable for humans at this point, at least. So it's like not something that would we would have good supervision on. And also, we now have these like benchmarks, like the frontier math that OpenAI showed some improvements on, like has extremely hard questions that you need to really be like an expert in the field to be able to evaluate whether the model is doing the right thing. So it's, yeah, it is a challenge. And I think we think that this will become more of a challenge as we go forward. We think that like as the models get smarter and we are trying to use them to do more advanced things, it will only be more difficult to evaluate whether what they're doing is good or not. And as a result, our techniques, like right now, the training basically relies on two things. We have outcome-based environments where you need to be able to just automatically grade what the model is doing. And that's possible in some cases, like the competitive coding, but not like for more general real-world tasks. And the other part is reinforcement learning from human feedback. And the main challenge is that the human feedback part, I think, will be increasingly more difficult as we go towards more and more advanced tasks for the reasons that I described. And then like the question is, and this is also relevant to online, because like you might ask questions of like whether this code is, for example, safe to run, or whether this action will lead to like good consequences in the real world. And again, as the models become smarter and smarter, it becomes harder and harder to tell like whether the response of the model is good, whether it's like harmless or whether it's like indirectly causing some bad actions and so on. Yeah, so that's the main core challenge that we are trying to study here. But the question is, how do we study this today? Because we don't really have like superhuman models. We have this, and this work has been done like over a year ago. So we didn't even have like O1 models at the time. But yeah, so we didn't have models that are extremely impressive in any given domain. So instead, we were studying an analogy. So the normal kind of machine learning setup is this, where we have a supervisor, which is substantially stronger than our model. So the supervisor is providing us labels, and we trust those labels to be good. We trust them to be kind of ground truth labels on the given task. And what we kind of care about ultimately is this problem that we call super alignment, where the model is in some sense more inherently capable than the supervisor. In some sense, is capable of producing better responses than the supervisor themselves. And yeah, and then the question is, can the supervisor still align and control this superhuman model? But yeah, so right now we don't have those models. So instead we are studying this analogy where the supervisor will make the supervisor really better than the student, and we'll try to see if the student can generalize beyond the supervisor. So basically, if the student can generalize the intent of the supervisor, understand kind of what the task was, and do better than the supervisor themselves. Okay, so in terms of like the actual experiments that we did, we define these several concepts. So we have a certain task that we will be trying to solve. It's going to be some kind of NLP task, for example. And then we have the weak model that's the supervisor. So we will take some model from the GPT-4 family. They have like a bunch of models at different sizes, just the pre-trained model, not RLHF. And then we fine-tune that model on some ground truth labels on the task, and we get a model at a certain level of capability. Because it's small, it's not going to be great, but it's going to try to solve the task. And then we'll use that model to produce labels on the held out data. We call that the weak labels. That's the labels that we're going to use to supervise a stronger model. And then the next model is the weak to strong model. That's we take a model again from the GPT-4 family, but larger, and we fine tune it on the weak labels. So we don't show it the ground truth labels for the task. We train it on the labels produced by the weak model. And then we are trying to see how well it performs. And finally, we also have a baseline of the strong model, like a strong seeding, which is we just train the strong model on the same ground truth labels. So what we are trying to do is we are trying to recover the gap between the weak model performance and the strong model performance when we supervise the strong model using the weak labels. So again, this is a weak model trained on the ground truth labels. This is a strong model trained on the ground truth labels. And this is the strong model trained on the weak labels, so on the labels that are produced by the weak model. And so we compute this measure of performance that we call PGR, or performance gap recovered, which is trying to capture how much of this gap in performance did we recover in the weak to strong state.
Just more practically, the weak and strong models, are they only differing in terms of the model size, or do you have other considerations?
For the main experiments in the paper, they were different models from the GPT-4 family, only different inside. But we actually had some experiments in the appendix where we use, where we come up with different ways of producing the weak labels. For example, you can start with ground truth labels, but then alter them in certain ways, like you maybe introduce errors that correlate with the length of the question or something like that. Basically, yeah, I can talk maybe a bit more about that later. But yeah, for the main paper, we just use different sizes of the models. Yeah, so the goal is to recover this performance gap recovered close to 1. And that would mean that we can elicit the full capabilities of the strong model on this task by only using weak labels, like imperfect labels from the weak supervisor. Yeah, and then if we could do that, then we could, if we could do that in relevant tasks, then I think that would be quite a positive update, because that would mean that we can generalize from human feedback on simple tasks, for example, or noisy human feedback on very hard tasks, to a model that's fully elicited capabilities on that hard task. So we can train superhuman reward models, for example, and then we can do reinforcement learning from human feedback and hope that it generalizes quite well beyond the capability of the supervisors. Or we could also just train some kind of safety classifier. So for example, we could have a classifier that looks at the responses of the model and tells us if the response is safe or aligned in some sense. And again, even if we cannot ourselves tell for the strongest models whether the response is safe or not, we can tell for simpler examples. And then if the safety classifier generalizes that supervision, then it would also work. So that's kind of the motivation. Okay, so I'll talk about the results of the experiments. We did experiments on 4 different groups of tasks, 3 NLP and 1 computer vision. I'll only focus on the NLP tasks for this talk. The first group is just the kind of NLP classification data sets. We take a bunch of standard NLP tasks and we convert all of them to binary classification. So the model is just outputting a label, just 0 or 1. We also have the reward modeling task, which is basically how we train the reward models for ChatGPT. You have some data set of human feedback telling preference between multiple possible completions for a given prompt, and we consider that task of training a reward model. And then we also did chess puzzles. So that's, you have some chess position and your goal is to predict the only move that is good in that position. By construction, there is only one move that is good. And that's actually a generative task where we have, you need to generate the actual string corresponding to the move. And then we finally had ImageNet classification, but I would not talk about that. And we use, again, the pre-trained GPT-4 base models. So no post-training, no RLHF. We just start with the base model, and we fine-tune that on the different labels. Okay, and we'll look at a lot of plots that look like this in this talk. So let's spend a little bit of time reading them. So here, the horizontal axis corresponds to the size of the model. It's in fractions. The 1 corresponds to the full GPT-4 size, and then we have different smaller size models in that family. And this is training flows. And the vertical axis will be test accuracy. And the black line will show the ground truth label accuracy, so the strong model seeding performance, how well you can do on the task if you train your model on the ground truth labels. And the different lines of different colors, they correspond to, actually before that, just to clarify, so this point on the black curve would correspond to the full GPT-4 trained on ground truth labels. And this size is roughly kind of GPT-2 sized, but obviously not it's not really GPT-2, it's just a small model within the family of models of GPT-4. Yeah, and then the lines of different colors correspond to the different weak supervisors. So if we take this bottom line, for example, all of the dots correspond to training on the labels produced by the weakest supervisor, like the GPT-2 here. Yeah, so basically this point corresponds to a GPT-2 size model trained on the GPT-2, and this point corresponds to the GPT-4 model trained on GPT-2 labels. And each point corresponds to like different size students trained with the same weak supervisor. Yeah, different lines correspond to different supervisors. Yeah, and then so we care about this performance gap recovered. So we want the curves to kind of slope upwards, which would mean that like the student is doing better than the supervisor. So in this case, GPT-2 trained ground truth labels is at around like 60 something performance, and the GPT-4 trained on GPT-2 is at around 70, while GPT-4 trained on ground truth labels would be at 90. And so we recovered this 10 out of 30% gap. Yeah, so the performance gap recovered would be roughly 25%. Yeah, and so yeah, we'll also look at just lots of this performance gap recovered. So it's the same structure, but just on the vertical axis we show the performance gap recovered, and we want those to be as close to 100% as possible. Yeah, okay, so this plot summarizes the main kind of baseline results that we have. Here we show the results for the NLP tasks, the chess puzzles, and the reward modeling. And the results are actually different between those different tasks. On NLP, we have the best results. So first of all, we get kind of pretty good PGRs on the task, so like between 20 and 18, and all of the slopes are pointing upwards. We get improved performance as the student size increases, even for a fixed supervisor size. So like we are able to do better and better as the student model gets stronger and stronger. And then for chess puzzles, it's kind of like intermediate medium results. The performance does improve initially for a fixed supervisor as the student size increases, but then it kind of plateaus and it doesn't continue improving. And the PGRs are kind of becoming worse. They recover less and less of the strong model performance for a fixed student side. Sorry, for the fixed supervisor side. And then for the reward modeling, we have the worst results. Like the curves are almost flat. There is some small improvement relative to the supervisor, but very small, and the PGRs are almost at zero. So we recover almost no performance beyond the performance of the supervisor. Yeah, so pretty different results in different domains. Universally, we have PGR between 0 and 1, but yeah, very different between different tasks. Okay, so that was the baseline results, just like what happens when we just directly train the student on the weak supervisor labels. And there we saw the results. But now I'll talk about a few kind of other ideas that we tried for improving the results. And one very simple idea is bootstrapping. So maybe instead of directly using the GPT-2 labels to supervise GPT-4, we should come up with some sequence of models like GPT-2 supervising GPT-3 and so on. And this is an idea that is popular in alignment, that maybe instead of like directly supervising a very superhuman model, we would supervise a slightly superhuman model, which would help us supervise even more superhuman models. And this is maybe like one clean setting in which we can try that. Yeah, and we do actually see that on chess puzzles, it kind of works. So here the dashed line shows the previous results that I showed with just directly training on the weakest model supervision, while the solid lines show what happens if we train in a sequence. Basically, we train here for this model, we train it on the supervision from this model, which was itself trained on this model, and so on. So we train the sequence of models. We start with the weak labels, train a slightly stronger model on those weak labels, and then we keep iterating like that. So yeah, so on chess puzzles, it actually kind of works. We are improving results quite substantially compared to the baseline. but it didn't work on the other tasks. So we tried it also on NLP and on the reward models, and there it didn't seem to help much. So it is definitely not like something that works universally. And another idea we tried was this confidence loss, which, yes, the motivation is as follows. So normally in this baseline experiment that I described, we use the cross-entropy loss between the student predictions and the weak model predictions. We use actually the soft labels from the weak supervisor. And the optimal thing that you can do in this case is imitation. So you can just predict exactly the same thing that the supervisor was predicting on this question. That would be like something that gives you zero loss. And at least intuitively, that's not what we want to do. We want our more like our strong student to be able to disagree with the weak supervisor. We wanted to be able to not predict the same thing because we don't trust the weak labels. They have errors. Yeah. And the idea is that maybe we can add regularization towards the strong model's own predictions. And yeah, we have a very simple instantiation of this idea where we just mix the predictions of the weak model with the predictions of the strong model itself with some like tricks actually. Like, so this f hat is the predictions of the strong model, but we go to like hard predictions, so zeros or ones, basically, yeah, zeros or ones instead of soft probabilities. And we also rebalance them to be class balanced within the batch. So it's kind of hacking. And I don't think that this loss is necessarily like what we would use to, align superhuman models. This is mostly just a proof of concept to show that you can actually do better than baseline in this setting. Yeah, and then here this alpha coefficient is something that increases from 0 to 0.5 during the training. So like initially the predictions of the student are just random, so we don't want to mix them into the into the labels, but by maybe like 20% of training, the strong model already has some idea of the task that we're trying to solve, and we don't want, like if it's very confident in a certain prediction, which disagrees with the supervisor, we don't necessarily want to override its confidence. Yeah, so that's the idea for the loss. You can also rewrite it in this way by like splitting the cross entropy into two terms. And the first term is our original loss, and the second term is just cross entropy towards your own predictions, but like a hardened version of them, which is equivalent to just a confidence regularization. So you are saying you are trying to increase the confidence of the strong model's own predictions. Yeah, so that's the second term in the loss. Yeah, that's the idea. And this actually works really well on NLP tasks. So on the NLP tasks, you can see that by using this loss instead of the baseline, we go from maybe like 70% PGR to something like 85 or 90, even when supervising the strongest, from 70% accuracy, 60%, 70% accuracy, 90% accuracy by even when supervising a GPT-4 size model with a GPT-2 size supervisor. And the PGRs go towards like 80 when we were previously sorted. So this really helps on the NLP tasks. And yeah, so here we show it's split across the different data sets that we use. And you can see that on most data sets, it helps quite dramatically. So here, but there are a few exceptions. So this is one of them where this loss doesn't help. So it's not universally something that helps. But usually when it didn't help, there was already something a bit weird about the performance. So for example, on this data set, the performance doesn't improve with the size of the model, even when you train on the ground truth labels. So there is maybe some something strange about the data set. But the big thing is that this still doesn't help on the reward models. So we tried this idea on the reward models, and it still doesn't really improve the performance gap recovered there. And that's actually probably the most alignment relevant task that we have. So neither of the two ideas that I described actually helps on the reward models. And that's still something that we didn't figure out to this day. Okay, so now I'll talk about some, yeah. Do you have any intuition for that? Yeah, maybe I'll talk about that a bit later in the talk. But if I don't, yeah, then please repeat the question. Yeah, so I guess, yeah, I'll talk about some experiments that we did towards understanding these phenomena. So first of all, when we train the weak model, sorry, the strong model on the weak labels, as I said, like the best thing that it can do is imitate the weak labels. So it should just make the same predictions as the weak supervisor, and it should eventually overfit. So if the weak supervisor is imperfect, it should also be imperfect in the same way if you train long enough. And so one question is, do we actually observe this overfitting in practice? And to some extent, we do. So here we show the fraction, the progress of training on the horizontal axis. So the fraction of an epoch that we have done. We only do one epoch of training. And on the vertical axis, we show the test accuracy. And you can see that for some pairs of student and supervisor, so the different curves correspond to different pairs of student and supervisor. And for some pairs, we have this kind of shape where initially the performance is much better than at the end of training. So like at this early stage of training, the student kind of figures out what the task is and it performs well, but then starts kind of overfitting to the mistakes of the supervisor. And actually, if we could do early stopping, if we could just figure out what is the optimal way, optimal point at which we should stop training, then we do get better results on the reward modeling task. So the dashed line is like our baseline, what we saw before, and the star lines are what we get with this cheating early stopping. But the thing is that in our setup, we cannot really assume that we can have access to ground truth labels, because we like the weak labels are supposed to be like the best labels that we can come up with. And so we cannot tell when to stop training. So this is not something that we could really do in practice, but it shows that, yeah, maybe part of what happens on the reward models is this like overfitting issue. But also there is another interesting phenomenon related to imitation. So we wanted to figure out how well does the strong student imitate the weak supervisor. And towards that, we decided to measure this agreement metric. So basically, what's the fraction of test data points on which they make the same prediction? And you can see, and we plotted again for all pairs of student and supervisor, like in the same way as we plot our other curves. And you can see that basically the agreement becomes worse as you increase the size of the student. So that's pretty unusual because that's a task that we train on. And like in a way, the performance on this task becomes worse with the size. So we have some kind of inverse scaling here, which is not something we generally see. And yeah, it's pretty unusual. So basically, what this means is that GPT-4 is worse at imitating GPT-2 labels than like a GPT-3 is. And yeah, and that's part of the reason why we see this weak to strong generalization in the first place, that the student is kind of not really able to imitate the supervisor, the mistakes of the supervisor. So here we also show the results for different, like, yeah, I think this is, I forgot what the plots is. I think this is on the correct examples. Yeah, supervisor correct, and this is on the mistakes. So, but on both actually, but especially on mistakes, we see that the largest models are really bad at imitating the mistakes of the small model, even though that's what we train them on. Yeah, and I'll talk a bit more about this in the end of the talk, but I think this is like one of the possible kind of issues with generalizing the results of this paper to like the thing that we actually care about, which is aligning superhuman models, because maybe superhuman models would be pretty good at imitating human mistakes. Yeah.
I'm just trying to understand this a little bit more, but isn't this, like based on just on a third graph, isn't this a good thing in the sense that whenever the supervisor, which is weak, is already making mistakes, I'm not saying that the student model is giving the right answer, but at least it's disagreeing, it's understanding that it's making a mistake and it's trying to be better at it.
Yeah, I mean, it's good in the sense that if this didn't happen, then we wouldn't get like weak to strong generalization. So Yeah, and one thing I forgot to say is also, so we have two sets of curves here. One is like the dashed lines are again the kind of baseline results, and then the lines with the triangles, the solid ones, are what happens when we use the confidence loss that I described. And you can see that with the confidence loss, there's like even less agreement. So it is doing what we wanted and like preventing it from agreeing as much with the supervisor. But even by default, like when we train GPT-4 on GPT-2 labels, you only get like 80% agreement. And yeah, so it's good in a way, but it's possibly bad from the perspective of like, is this like a good reason to get weak to strong generalization? Because like in the future, like will the strong models also not be able to imitate our mistakes, or is this just an artifact of the setting that we are studying? So I think that's a possible issue here. Yeah. Okay. So, the next thing that I want to talk about is salience. So one way we think about weak to strong generalization is we think it can happen because the concept that we're trying to elicit from the strong model is kind of salient for the strong model. So there was this result like back in GPT-2 times maybe that, or even before then, that if you just train an RNN on reviews, on like Amazon reviews, then naturally there are neurons that encode sentiment. I think, yeah, the result's called like sentiment neuron. Even though you didn't train for that task, that representation naturally arises in the model. And like GPT-4 definitely has a very good representation of a sentiment of like a certain text, even though it's pre-trained in kind of a unsupervised way. It's not trained to predict the sentiment, but that representation just arises naturally, and we expect that that should hold for many relevant concepts, like in particular maybe for truthfulness or for like safety of some response and things like that. And so then if that's the case, then it should be much easier to elicit kind of the true concept of sentiment, for example, from the GPT-4 compared to like what a GPT-2 size model would predict as sentiment. And yeah, so that's one of the hopes and one of the reasons we think we get this weak to strong generalization. And so in the next couple of experiments, we'll be trying to look into this salience thing. So like how salient are the concepts that we're trying to elicit for the for the strong models. So here we do a few shot experiment where we just prompt the strong model with a few examples of the task. I think 5 examples in this case. I believe this curve shows. It's few shot and zero shot, and this is fine tuning. And you can see that basically even zero shot, the models are kind of reasonably good at the NLP tasks in particular. And then with few shot, for the largest models, they are kind of getting actually pretty close to the fine tuning performance. So in a way, a lot of the NLP tasks are just like very natural for the models and very easy.
So the shots are still from the ground truth, right? Or is it from the labels on the week?
This plot is on the ground truth labels. But the next thing, is we can also just repeat the experiments prompting with the weak labels. And that's what we show here. And so first of all, we kind of reconstruct the result that we got with fine-tuning, but with prompting. So here, like the different curves correspond to prompting with weak labels from different supervisors, and you can see that that's kind of in between what we get zero shot and what we get prompting with ground truth labels. So we also can introduce like a notion of performance gap Ricard or PGR. And also we can compare the results to what we get in fine-tuning. And actually, on some tasks, this prompting is for the largest models, or like for pairs of models where the student is the smallest and the student is the largest and the supervisor is the smallest, prompting can actually be better than fine-tuning. But with the confidence loss that I introduced, we can do still even better. So So in a way, I think the conclusion from this is just that at least the NLP tasks are relatively kind of salient in the model and like relatively easy to elicit. You only need a few examples with ground truth labels to elicit really good performance on them from the largest models. Yeah. Okay, and then so maybe coming back to the question about why it doesn't work as well for reward model. Like one hypothesis can be that it's related to the salience of the reward modeling task. So the reward modeling task is you show the model a completion to a given like ChatGPT style conversation, and you're asking, is this a good completion or not? Or like maybe relatively, which of the two completions is better? And the completions are generally kind of similar quality. They're either both really bad or both really good. So these like human feedback data sets are very noisy and very hard to tell which one of them is actually better. And yeah, and so it may be that this task is just not very salient for the base GPT-4 model before you do like any fine tuning on, you know, conversation GPT-4 style, ChatGPT style conversation. And so what we tried is maybe we can increase the salience in the same way as like in this sentiment neuron idea that I described by just fine-tuning the model in an unsupervised way on all of the conversations from the you know, reward modeling dataset. So instead, so we are not using any of the labels, but we're just taking these conversations, both good and bad, and we fine-tune on all of them. And maybe like there will be some better representations for predicting what is good and what is bad. Yeah, and so we tried that, and it does in fact improve the PGRs. So in particular, it just lifts all of the curves upwards. So both the base model and the both the kind of strong models and the weak to strong models are all doing better, but also the PGRs are generally better. And if we combine this generative fine-tuning idea with the cheating early stopping idea that I also described, we get towards like 30 to 40% PGRs, which is kind of closer to what we get on the NLP tasks. So yeah, I think this is all not very satisfying as a resolution of the reward modeling results. And I think we still don't think that we have a way of getting good weak to strong generalization on reward modeling. But yeah, so at least I think this provides some insight into like our thinking on why this happens. Okay, so next I'll do some discussion. So there are a few limitations, I think, of the work. One is that we are focusing on this like really simple single forward path classification problems, while now maybe like the most exciting things is this generative tasks where the models generate long chains of thoughts and like produce some complicated reasoning. And it would be very interesting to repeat some of these experiments in that setting. Another limitation is that currently kind of most of what the strong student models know comes from like the pre-training on human generated data. And so like the strong models are already trained on like human level data in some sense. And then when we fine tune them on weak labels, like they just have directly absorbed data of like higher level of capability. And so that's possibly a large reason why we see weak to strong generalization, which may not hold in the future. In the future, maybe our main hope is that the models will just have really good representations or like understanding of certain concepts, and that's why they would generalize in the desired ways, but that's not directly what we're testing here. Yeah, and then the last issue is I described this thing that we are not getting good imitation. When we train GPT-4 and GPT-2 labels, it's actually pretty bad at imitating them. And we probably shouldn't expect that to hold in the future for superhuman models. They would probably still be quite good at saying like what a human would have said to this question. So if a human has certain bias or errors, the superhuman future models would probably be able to predict that. And so we cannot rely on the strong models just not being able to imitate our mistakes in the same way that we did in some of these experiments. Okay, yeah, and then I guess so this work happened before like the O1, and I think just I was trying to think about what kind of my updates are based on that. I think one is that, again, yeah, the fast progress is continuing. We are seeing this like major improvements on benchmarks, even like since GPT-4. And I think we're basically at the state where like for any given benchmark that we have, we can probably do well on that benchmark if we like put enough effort into that. Yeah, and then the models are kind of approaching the best humans in certain domains like competitive coding, like or competition math even. And yeah, so this problem of how do we do supervision to those models is relevant outside of domains where we just can automatically grade the outputs. And then the models are also producing these like really, really long chains of thoughts. And I think, yeah, one question is, yeah, and those chains of thoughts are also not, we do not have human supervision of them. So they're just like arise from the reinforcement learning. And yeah, so we wouldn't be able to get good human supervision on those chains of thoughts because they're so dense and so long. And yeah, so it's unclear how to grade them. And there's another question, like maybe one way you can think of, ensuring alignment of those models is by reading those chains of thoughts with some kind of automated procedure and telling if there is anything suspicious, anything bad in the chain of thought. But then there is also a question of, are the chains of thoughts actually faithful to what the model is trying to do, especially if we would train with some kind of supervision on the chains of thoughts, the model would probably try to conceal like the things that they don't want to show from the chain of thought anyway. Yeah, and then I think the big question is, can we generalize beyond these like constrained domains where we have like easy to compute rewards? So beyond like mathematics with numerical answers and beyond competitive coding, can we generalize to some fuzzy tasks? And I think that's where like this weak to strong generalization maybe is most relevant. So like if we have some question that's kind of fuzzy, so maybe like questions about policy or questions about like certain decisions that happen in the real world, where like we cannot provide reliable supervision on those problems from humans. Like we cannot say which policies are good or bad, but like can we still expect that these hard reasoning models would do well on those problems, or can we train them to do well? I think it's a very interesting and unclear question. And maybe like one way in which we can think the models would generalize is if you can break down this like hard fuzzy question into like first a hard but crisp reasoning problem where you just think about something objective, like what are the objective outcomes that would result from like implementing this policy, and then you in the end arrive at something that humans could actually evaluate. So maybe you arrive by doing a lot of kind of complicated reasoning, you arrive at like, this is what the state of the world would look like after we implemented decision. And then like for that state of the world, like humans would be able to like tell if they like it or not. Even though they couldn't tell from the beginning, like this policy is something we should or should not implement. And so maybe there's hope that we'll get weak to strong generalization in that way. Like we only have human, supervision on have easier examples of like human preferences or where you don't require this like complicated reasoning. And then you have really good reasoning skills. And by combining those two, maybe you can arrive at superhuman performance on like fuzzy examples that is still aligned with human values. Yeah. Okay. And then, so in summary, the main result of the paper is that we introduce a setting of weak to strong generalization, which we think will be quite relevant in the future, because like the main reason is that it is getting increasingly hard to provide useful feedback on like at the frontier of the model capabilities outside of very isolated specific domains. So we think this is an important problem. We only did like very toy version of the experiments in this setting, but we think the setting is like the most interesting part here. And like in our toy setting, we can elicit capabilities that are stronger than the supervisor capabilities, but we are still not able to get like to the full performance ceiling of the model that we could get if we train directly on the ground truth. And there are like many open questions of how to generalize this to like what the settings that we actually care about, like how do we remove the remaining disanalogies between what we are doing and the setting that we care about. yeah, and how do we think about this vector standardization with more modern, reasoning models? Yeah, yeah, that's it. The generalizable to what?
So like larger models with pretrained
Mhm.
simple small ones.
Mhm. Yeah. And like I guess that's the reason why in all of the experiments we like consider a whole bunch of student and supervisor pairs. So we have like a whole range across different capabilities and like gaps in capabilities between the student and the supervisor. So we're hoping that at least we can see some trends this way. But I think like there are major like transitions. So like when we go beyond, like right now, all of these models are below like the level of pre-training data, basically. Like they are not as good as humans who generated the pre-training data. But like once the pre-training, like once it is, we remove this analogy, and once like maybe if we pre-train GPT-4 on GPT-2 generated data only, and then we repeated the experiment, it's unclear if we would have the same trends. I think that's very possible. Yeah, that like something changes as we like go towards more realistic scenarios. But I think yeah, that's something that we would want to figure out.
How is this related to test time scale, like the difference between GB4 and GB401, right? So I think for 01, you're not giving all the type labels for 01, just like do some like test time scaling and like try to like elicit the CPU process or yourself. Like looking at this how can they combine them together?
Yeah. I mean, they are still like if you look at the DeepSeek R1 paper, for example, then like in there, they still need problems and like answers to the problems, right? And like then you are basically training the model to produce that answer on the problem. Like at least for math, for like coding, you have some tests and your solution should pass the tests. But yeah, I think the most analogous thing, if we just wanted to repeat this experiment in that setting, would be you have some data set and you just have like incorrect solutions to some of the math problems, maybe. Like, but maybe not just arbitrarily incorrect, but some kind of with some systematic errors. Maybe somebody like, I don't know, doesn't know how to multiply properly or like something like that, such that the model could learn to imitate that mistake. And then we can have some data set of that form where we have math problems with solutions that are like mostly correct, but sometimes incorrect answers, I mean. And then we are training on the data set and we are trying to get the model to like ignore the mistakes. We want to be able to train even when some of the supervision is incorrect, basically. Yeah. But I think also like what I tried to talk a bit about towards the end, where like I think we can get really good supervision on crisp, kind of easily gradable tasks like math with answers and like coding competitions where you have tests that need to pass. But it's much harder to do that style of training for, some fuzzier tasks where you don't know what the correct answer is. There isn't like a single correct answer. There is no way of telling that, oh, this response is good or this is bad. And that's where like RLHF is what we did historically. But like, yeah, then the question is, how do you do RLHF when the outputs are very, very complicated and long and hard?
Just something on the points that you mentioned. I'm just trying to compare it, like this setup where you have like a weak supervisor with something like taking the ground truth and randomly inducing some errors in the ground truth itself. What I'm supposing is that would be an easier setup because the model should be able to generalize better from some random noise
Yeah.
versus like a systematic
Yeah,
error that's happening in the week. So I'm just wondering if like there's any study done in terms of studying how much of the weak systematic error was like corrected in this process.
Yeah, we actually tried to think about it in this way where we kind of, where we basically, if you can split your errors and your labels into some kind of signal and noise relative to the student. So if there is some kind of imitable, like mistakes that you can imitate and mistakes that you cannot. And if you can easily imitate the mistakes, then I think by default, you would not get really good with the strong generalization. I had some plot of this somewhere in the paper. So we did some synthetic experiments where we like introduced the mistakes synthetically and in different ways, ranging from completely completely easy to imitate to impossible to imitate. I think this is the figure. And basically we get very different results in those two settings. So I think this plot is where it's very hard to imitate the mistakes. So in this case, if you train on the you basically recover good performance when you train on the hard to imitate mistakes. But when it's very easy to imitate the mistakes, like this plot, then you get this completely flat curves. So you just like you want to do exactly the same thing as the supervisor. And so we think that maybe the real scenario that we are in is some kind of mixture of those two. So it is basically a mix of like a bias and noise. And like you remove the noise, but there is still the bias, basically the part of the mistakes that is easy to imitate for you. And you ideally want to unlearn that.
So I'm basically looking at supervising and then how that short models are really crowded. So I was wondering, like, for example, like with like would it work better for example, science task where you have like a correct answer and a correct reasoning task? Maybe for social reasoning, like for instance, like multiple ways of interpreting the same thing, but like they're subjective in interpreting like that. Would that be part of the models? And if so, how can we improve the learning mechanism?
I think that's like so basically I think with the current O1 type of models, we are able to improve a lot on this like hard reasoning tasks where there is objectively like one good answer, and it's very easy to tell which answer is good and which answer is bad if you have the ground truth, basically. But then like I think they still don't give you a way of doing really well on this like more subjective or maybe more fuzzy tasks like the social reasoning. And I think that's where we would need vector strong generalization to work in order to supervise models to like elicit their strongest capabilities there. Because like if it's actually some like extremely hard question where like a human is unable to fully think through it and like provide a very good answer, we cannot reliably create like the outputs of the model, and we need to generalize from like easier examples to harder examples. So I guess like in general, this paper is not like a method. We don't have a method of doing this. It's more about a setting and like setting up a problem that we think will become increasingly important, and like just doing some experiments to start thinking about it. But I think that's where it would be most relevant in my opinion, like those kind of fuzzier reasoning tasks, and also like things related to safety and alignment, where again, it's maybe not objectively easy to tell what is good and what is bad.
I have one last question. What do you mean something like so? What do you mean if you file that?
I mean, I'm not at OpenAI anymore, so I don't know. I don't think I think it's just a matter of when they decide to call the next model like GPT-5, right? Like when it's good enough for them to call it GPT-5, because they had new models since GPT-4. just call it for all one.
How would you analyze this organ and we organize the channel within that? Yeah. You see, code 3 is the first module which